A capacitor is like a battery. It is an energy storage device, a rechargeable one, but it is extremely short term, quick to charge, quick to discharge. We're talking less than a second. It's also much more expensive on a per energy unit basis and much larger than a battery, so that's why they're not used as batteries. It's just like everything else in life, there's trade-offs. Capacitors are two-terminal devices. They come in two types, nonpolar and polar. Nonpolar capacitors can be charged and discharged in either direction. They're very open-minded that way. Polar capacitors, you always want to have positive here and negative here. When you charge them, you put positive charge in here, you put negative charge in here. When they discharge, the positive goes out here and the negative goes out there. If you hook them up in reverse, bad things happen. Polar capacitors are usually called electrolytics, which means when you hook it up the wrong way, or the capacitor just gets old, you have electrolytics all over your PCB. So why would you choose polar instead of nonpolar? What are the trade-offs here? Cost, basically. There are some trade-offs based on size and amount of capacitance, but there are much more expensive nonpolar capacitors that can match the size for the same capacitance of the polar ones. The polar ones are just cheap. That's why you see them all over the place. And it's a very common point of failure for old computers, such as one particular example I know of is some of the old all-in-one Macintoshes back in the good old days. You know, the beige toasters. It was quite common in them to have to replace capacitors to get them working again. So whenever you see polar and nonpolar in a circuit, generally the reason is for cost. And the reason for specifying it's a polar is just to make sure you don't hook it up the wrong way. There is no situation whatsoever that you couldn't take a polar and replace it with a nonpolar. It'll just cost more. And depending on how you make the nonpolar one, it might be a different size. So what on earth is a capacitor anyway? It is a sandwich. So let's imagine you have a wire. And the wire is going into a conductor. It's a conductor, just a chunk of it. Let's just say it's a metal plate. And down here, you've got another conductor, another metal plate, another wire. What's in here? An insulator. It could be plastic. It could be air. The electrolytic capacitors use fancy chemistry, which I won't get into right now. But it ends up being roughly the same effect. But in here is just an insulator. That's all it is. That is literally all you need to make a capacitor. Of course, to make a good capacitor, to make them different sizes, different capacities, you need special engineering. But anytime you have this, you have a capacitor. Conductor, conductor, get your ticket out. Non-conductor, he doesn't want your ticket. So for example, if you have two wires, well, you have conductors, each wire is a conductor, and between them is an insulator. This is a capacitor. Of course, it has to have charge, or rather you can apply charge and it will have capacitance. And that is actually one of the cool but really annoying things about capacitance in general. Anytime you have two conductors, that's not a conductor between them. So any two conductors that just happen to be nearby. It's sort of like how wires have resistance and we ignore it, but it's really there and it sucks. But obviously that's not something we can get rid of. For example, high power lines. You've got two wires carrying huge amounts of voltage and current between your house and the power company. And there's capacitance between those wires. And that's one of the things they have to engineer for. But we're talking about the little device you plug into your board here. Just like the resistance of a wire, the capacitance between different parts, between the traces on your PCB and all that, except in the most high frequency, high latency sensitive, basically high parameter applications. That's when things like wire resistance, capacitance between parts, temperature starts mattering. But as usual, 99% of the time when you're doing regular stuff like this, you don't have to worry about it. So a capacitor is just a device like any other. So what happens? Well, let's illustrate with a circuit. Let's put a power supply here, a capacitor here, and a resistor here. And right now, nothing's connected. Nothing at all is happening. I will now connect the power supply to the capacitor. And this is a non-polar capacitor. So if it were a polar capacitor, good, bad, good, bad. Non-polar, we don't have to worry about it. So what is happening right now as this current is going through? And of course you'd want a resistor here to make sure it's not a short circuit. Don't worry about it. So what happens? So you have an electric field. The negative electric field spreads along here to there. The positive electric field spreads here to here. because this side has positive charge, this side has negative charge. So this side is trying to push electrons out, this side is trying to pull electrons in. But there's an insulator in there. This is technically an open circuit. It's not connected. So what happens is this electric field is basically pulling, conceptually, and this is basically pushing. So it's trying to shove electrons here in, it's trying to pull electrons out there. And current does flow briefly because the insulator is just thin enough. Because if you have a big, huge gap, you're just going to get an open circuit. Technically, it's still a capacitor, but it's a capacitor of such low capacity that every once in a while an electron will deign to notice it. But if you have very, very thin insulator, that's just enough to make current not pass through, but not anymore, which is why capacitors have a maximum voltage rating. If you go over that voltage, the insulator won't be good enough and it'll start going through. But if you don't exceed the voltage rating, then it will not have more than a minuscule trickle current going through, because it's an insulator, but charge will still be able to reach each other over the gap. So basically what happens, if we draw the capacitor again, we have our conductor, and insulator. So what happens is the force being exerted, the conceptual force, not Newton's, the conceptual force being exerted by the electric field, trying to push electrons into this end, trying to pull electrons out of this end, is enough. There's enough going on with this thin insulator that it pushes electrons away from this side, because they do have somewhere to go. It's an open circuit, but they do have somewhere to go. See, because this is a big old conductor. It's got room. If you force them in, it doesn't want to. If there's no voltage, if there's no pushing, they're not going to go in because everything wants to be nicely distributed and electrically neutral. But you're applying this field, so there is enough to push some in. So this becomes negatively charged and it pushes electrons away and they go into the positive end of the battery because it's pulling. They do have somewhere to go, but only to a point. So what happens is this thing charges. Electrons get pushed into this end and stay there. Electrons get pushed out of this end and stay out. All right? And then once the capacitor reaches the same voltage as this, nothing happens anymore. In fact, it happens more slowly as you go on. When the capacitor is completely discharged and you hook up the power, it goes and charges a whole lot almost instantly. And then a chunk more, and then a smaller chunk and a smaller chunk, and then like 5 minutes later, it's going to be like... So it technically never charges completely, but it charges almost completely immediately. And you'll find on the datasheet for capacitors, there is a particular number that tells you when, like how much time, how much voltage to get to a certain amount of charge. There's a standard number, which tells you roughly how fast it charges and discharges. Now here's the fun part. Here's why it holds the charge. So what we've done is we've pulled electrons, we've pushed electrons, and now there's a difference because of the pushing. Even though there's an open circuit, they're close enough together to exert enough force on each other to attract each other. So cut the power real quick and don't discharge. So the power is gone. The power supply is still charged. Let's assume it's a battery or something, but it's an open circuit, so it's not doing anything anymore. This one's also a completely open circuit. Technically, again, this is a capacitor. You can see capacitors everywhere, but this is way too big. It's just an open circuit. So this end has a negative charge and this end is a positive charge. So of course they want to spread, but now there's an open circuit. The conductor is much, much less accommodating of that. You know, you can only shove a little bit back out before the wire is not accepting any more, is not giving more electrons here, is not taking more electrons there. So what happens is you have this capacitor maintains its charge, and the funny part is they're attracting each other. See, they're repelling each other. The electrons are repelling each other. The positive charge part is trying desperately to suck in anything it can, but they're also attracting each other because positive and negative attract. So while they are trying to pull things in here to equalize, to spread out there and push them out to equalize, let me not dump the nails again, they're also stuck to each other over this thin dielectric. So when you disconnect the capacitor, it stays charged and it very slowly discharges because electrons, like everything else, are messy, and every once in a while an electron is going to just jump out of the pin of the conductor or just randomly go somewhere, or it might go across the insulator a little bit, trickle charge and equalize that way. But capacitors stay charged. They stay charged sometimes for years if they are large and high quality. So this is why it's dangerous. You might see electrostatic discharge or other electric shock warnings when opening a device that's not plugged in. When you unplug it, there are still capacitors, especially if what you're unplugging is a power supply, like a power supply for a computer or a wall wart. Those will have capacitors in there for smoothing out the voltage, and those capacitors can stay charged. And if you touch them, woe be unto you. But that's why that warning is there, because even though the charge is trying to get away, it's also stuck to itself. So a capacitor stays charged. Now let's make a change. Right now we have a capacitor that is charged from the power source. Now let's connect it to the resistor. And unsurprisingly, it discharges through the resistor. And this is the safe way to do this. If you have opened something that has capacitors that may or may not be discharged, you just take a resistor, hold it in, something that's got a rubber grip so you're not touching it, and you just touch the resistor legs to the sides of the capacitor. And the capacitor will discharge through the resistor. The resistor makes sure that not too much current flows at once, and it dissipates it as heat until the capacitor doesn't have enough voltage left in it to worry about. But this is where it acts like a power source. There's a positive charge here and a negative charge here that was applied by the battery, and there you go. That's a voltage, and so current flows. And as the charge equalizes, as the electrons flow out and back in this end, the difference becomes smaller, therefore the voltage becomes smaller. So the voltage goes down and down and down and down. Now what if we do this? What if we connect them in parallel? Well, let's assume I just did this. I just connected the power supply, I just flipped the switch. The capacitor is uncharged. Nothing is flowing through the resistor. The electric field is establishing itself. So the first thing that happens is this capacitor greedily sucks up the power it can. So you have this positive charge, this negative charge here, is basically going into charging the capacitor. And the resistor is getting almost nothing. But the more charged this becomes, let's say this is 5 volts. Let's say this is charged to 4 volts, right? The difference is only 1 volt now, because it was 5 to 0, so that's a full 5 volts, so it's all going right in there. But 5 to 4, that's only 1 volt difference. So there's plenty left over. So as the capacitor is charging more and more slowly, more of the current is making it through to the resistor. And once the capacitor is essentially fully charged, it's just sitting there, charged but doing nothing, and it's as if it's not even there. And you've just got your power supply and a resistor. So what's the point of this? Well, one of the things is for smoothing out power. And we'll go into this in another video. But basically, if I take the power supply out, now, because see, the positive was here and it's positively charged there. So now the resistor is getting power from the capacitor. And it doesn't last long. It lasts an instant. Or you can have more capacitors and it'll last longer. But let's say that the power was gone for just a brownout, right? The power company all of a sudden had a lot of demand and then it equalized out. Because they have things that ramp up quickly when demand is high for just an instant. So all of a sudden, 18 people all turned on their washing machine simultaneously and the power supply went "Mrrr." But then the secondary generator kicked in at the power company and shoved a bunch more power in there. And then the washing machines were all nice and stable, and so it turned off the extra generator. For that instant, this capacitor was supplying the resistor instead. And technically the capacitor was trying to charge the power supply. That's easy to fix. To make sure it doesn't flow backward, you can just stick one of those in there. So when the power supply goes away, the capacitor tries to charge the power supply, the diode holds up the big stop sign, says you're going the wrong way, turn around. So it goes into the resistor. We'll go into more detail about how capacitors are actually used in circuits like that at another time. But that's basically how capacitors work. It's a sandwich with an insulator in the middle, and the insulator is thin enough that you can actually push charge against it. The electrons are not going across. The electrons are not actually, some of them are, just a tiny bit. There's a trickle, but for the most part, the electrons are not actually going across to the other side. But they're close enough, because this is so thin, that they're actually pushing electrons out, because there's too many electrons, it shoves them out into the positive. That's the magic of a capacitor. Now, there's one tiny thing. Now, what's going to happen if I do this? Well, the negative electric field is going to push electrons out through here, through the resistor, into this side of the capacitor, which is going to shove electrons out of this side and into the positive end of the power supply. So current flows until the capacitor is charged. And as it's charging, it'll flow slower and slower, because let's say you have 5 volts here, and eventually you're going to get 3 volts here, and then you're going to get 4 volts, and there's going to start to be no difference, which means current doesn't flow. It's trying to push through, but it can't. So if I just leave it like this, the capacitor will charge, and while it's charging, current will flow through the resistor and go down and down and down, and then eventually current will stop. And if I turn the power supply around, then all of a sudden it's going to discharge in the other direction, charge back up, and stop. So that's why they say that a capacitor blocks direct current, but it passes through or shorts alternating current. If I have this, then the capacitor will make slight variations based on its delay. It'll charge and discharge, but for the most part, the capacitor doesn't exist in this circuit. It's just a wire, because the alternating current, remember, it goes this way, then it goes this way, and it goes this way, and it goes this way. So 50 to 60 times a second, the capacitor is charging one way, then discharging the other way and charging that way, and discharging that way and charging the other way. So if you put a capacitor in series with alternating current, it essentially does nothing other than slight variations in the voltage curve. But if you do direct current, then the capacitor will eventually block. That's why you see capacitors in parallel almost always. There are reasons to have capacitors in series. There are reasons to use capacitors in alternating current. But pretty much I'm not going to worry about that until some random point in the future where I need it. For right now, capacitors are a thing you connect in parallel to decouple, to smooth, to whatever, and we'll go into good examples of how that works in another video. For now, I'm simply going to demonstrate capacitors. So I have here my power supply, which is already supplying, well, it will if it's connected to anything, 1 milliamp up to 5 volts. Now you shouldn't do that, that's dangerous, but 5 volts and 1 milliamp isn't that much. So it is relatively safe. But the reason I'm doing that is it's going to make it easier to show the charging of the capacitors. So we have here some non-polar capacitors. These are very small, 10 nanofarads, 22 picofarads, 10 picofarads. So we deal with volts in the whole numbers, up to hundreds of volts. We deal with, milliamps, sometimes microamps, sometimes full amps. We deal with hundreds, thousands, and millions of ohms, but farads, as it turns out, just the way the math works, 1 farad is gigantic. Like the biggest capacitor I have, and of course you can get giant capacitors, but the biggest one, the very biggest one, is only 1 millifarad. And here they are. They are as long as the first joint of my finger almost. And you can see it's pretty big in the breadboard. This is a 1 millifarad electrolytic polar capacitor. It's got the little minus symbols that you probably can't see. Thank you, Chinese camera. And if you look at one of these, you look at the top, there's a plus sign. It's not actually indicating anything with polarity. That's a pressure release. That is where the metal has been thinned so that if pressure builds up inside, it will more gently pop at the top and spill out rather than building until a stronger case just explodes. These are the ones that if you connect them wrong or you just use them for long enough, they will start spilling out. Anyway, the negative is marked on this one. The longer pin is positive. It's similar to LEDs. So there's our polar capacitor. The non-polar capacitors I have are much smaller. This one here is 100 nanofarads. And the non-polar capacitor has a limit of 50 volts. The electrolytic capacitor has a limit of 25 volts. If you go over that, you will have more trickle current and it'll break through. So I'm going to demonstrate charging. Now what's going to happen? Remember, I connect my power supply. These are discharged. These are discharged. So my power supply is currently delivering 0 volts. It says 5, but it's not really. It's going to immediately go down because it's going to limit it to 1 milliamp because there's no resistance here. This is a short circuit. So if I connect the negative power to one side of the non-polar capacitor, so it doesn't matter, and then the positive, the voltage is going to climb and climb until eventually it'll reach 5, it'll stop, and this will go down to 0. It'll stay at 1. So it's turning the voltage up and voltage up. But what happens? So when I'm going to connect this, it's immediately going to draw lots of current. And this thing is going to say, hey, he wants a maximum of 1 milliamp. So it's going to turn the voltage down real quick to make sure only 1 milliamp is flowing. But then the capacitor is going to charge to whatever voltage that is and stop drawing current. So then this thing is going to say, oh, it's not drawing 1 milliamp. Let's turn the voltage up. And then the capacitor will start charging, drawing way more current, and it'll say, oh, wait. But then it'll charge to that voltage and stop drawing current again. So the capacitor is kind of like, wait, okay, I'm good. okay, I'm good. And the power supply is like, here you go, wait, okay. Okay, here you go, wait, as they're kind of fighting each other until they charge. So let's watch it happen. And my demonstration failed on this capacitor because it's so small, it charged quickly enough that this never had time to turn the volts down. So let's do it again. This one I've already tested. I know we can see it happen there. But let's just quickly charge. So I do this, and I do this, and the capacitor's already charged, so I take it back out. Now watch the LED. I'm going to connect the side I connected to positive, because it's a non-polar capacitor, but this is the side that has the positive charge. And I'm going to connect the negative, and to make it slightly easier to see, let's operate in low light conditions. Watch the LED. Did you see it flash? Let's do it again. We'll connect the positive to the capacitor, and the negative, and now it's charged. We'll take it back out. The end I charged to positive to the LED, and then the end I charged to the negative of the LED, and we get a flash. So the smaller a capacitor is, the faster it is to charge and discharge, but the less energy it has. So it has a faster response, we would say. This will come into play in the next video. Larger capacitors hold more, but they respond more slowly. So they take longer to charge, which means they're gentler on the circuit. They pass voltage through more easily to the rest of the stuff. They discharge more slowly, meaning they last longer, but they don't start and stop discharging that quickly. Whereas this one doesn't hold much, so when it's gone, but it'll happen very fast. So you use a combination of big and small to smooth out all the different stuff. So now, what I was actually hoping to demonstrate, now we're going to charge this other one. Now, this one is polar. We have to charge it the correct way. It will charge the other way, but it will also break. So watch the voltage. It drops down, and it's going back up at 1 milliamp. See, nice and slowly. And then when it reaches 5, it's charged. So this capacitor is now charged 99.999% of the way to 5 volts. So 4.9999 volts. And if I leave it here a month, it'll probably get close enough to 5 that I can't measure the difference. But the point is, it's now charged. So it kept turning up the voltage, and the capacitor would charge to that voltage and turning up, maintaining that 1 milliamp until it reached the full, and then pretty much no current was flowing. So now I'm going to discharge this capacitor through the LED, and this one is a higher capacity. So this one was 100 nanofarads, this one is 1 millifarad, so that's a big difference. So 100 nanofarads is 0.1 microfarad, which is, divide that by 1,000 again, and you get millifarads. But it's still big enough to have an effect in a circuit. But if we connect the positive end of the capacitor, and you notice it's staying charged because those currents are stuck to each other. Positive charge end to the LED, and the negative to the LED. Did you see it fade out? And did you see just now, can you see it blink on and off? How slowly, because the more it's discharged, the less of a difference there is, so it's very trickle charging. So let me charge this capacitor again, and we're going to do it with the lights completely off, which is going to be interesting. It would be easier if I had a switch hooked up. So now we get to watch it charge again. So it immediately went down. See, I hadn't fully discharged it, so it started at like 2 volts. And there you go. So that's loose. Now, I'm going to connect the positive to the positive and the negative. And here's how I'll do this, because I think I can reach the light switch while holding this near. Yes, I can. So here we go. Let's try that again. Here we go. And you can see, still on. I really hope that this is showing up in the camera. I'm not 100% sure it is, but it is still on. Still on. And it's getting dimmer by the moment, but it's getting dimmer more slowly. Because of the LED's forward voltage drop, because it's drawing less current, because of all kinds of factors. If you couldn't see that, take my word for it. But this is an illustration. This capacitor still has charge. In fact, this other capacitor probably still has charge. So I'm going to connect them to a resistor. So one end of this other capacitor, the smaller one, to one end of the resistor, and then the other end of the capacitor to the other end of the resistor, and now it's just charged. Because the resistor does resist the flow, but it scales, basically, by Ohm's law. It doesn't really taper off anywhere near as much as the LED, because the LED has its voltage drop and so forth. So we'll connect this, and now we're discharging the capacitor through a resistor. The resistor is nonpolar, so it doesn't matter which way we do it. So do that, wait a couple seconds, and you're good. Now, of course, it is still charged, but it's charged to such a small degree that it can't even overcome the resistance of my fingers, and even if it did, the current is so tiny because it's got so little power in there. So that's capacitors, and now let's go back to being safe, turn the current down, and turn it off. So that's capacitors. You charge them, they stay charged, and they discharge. Bigger capacitors will charge and discharge more slowly, but they have a higher capacitance, in fact. Smaller ones have a faster response, but lower capacity. Put them together and you have the best of both worlds. In the next video, I will show you how they are used to smooth out voltage in power supplies and similar things. They can also smooth out signals, anything that varies. You might say that a capacitor resists changes in voltage. So the more capacitors you have in your system, the harder it is for your system to change its overall voltage, which is good if you're trying to supply a steady voltage. But it's bad if you have signaling that it's like 5 volts is 1, 0 volts is 0, so you're switching it all the time. Remember where I was talking about how you have capacitance everywhere? If you're switching with very low power, if you're switching with very high frequency, that capacitance starts to matter. It resists the changing. But we're not working with gigabit Ethernet here. So for us, it doesn't matter. We're making logic gates, we're doing whatever. Capacitance is going to be ignored. But until that video comes, be seeing you.